Okay, we're ready now to talk about meta-analysis. This is a type of study that some people consider the very peak of evidence-based medicine, the highest quality evidence you can get, even above that of a randomized controlled trial. I am not necessarily one of those people. I think there are a couple of different types of meta-analyses. Some I describe as fondues and some as clam chowders, and hopefully by the end this will make some sense to you as well. So what are our goals to describe meta-analysis? A meta-analysis is a study of studies. We'll show how to tell if combining a bunch of studies is a good idea and remind you that the whole is not often greater than the sum of its parts. So let me give you an example of how we might combine different studies. So let's say we're interested in the high school graduation rate in the United States. And every state measures its own high school graduation rate. And so here are the high school graduation rates for a variety of states. They're just listed alphabetically here, and you can see now, how would I combine these numbers to get the high school graduation rate for the entire country? Well, intuitively you might think, well, I'll just average them, right? Just add them all up and divide by the 50 states and we're done. But that's probably not quite right? Because some states are smaller than others and some states are bigger than others, and California has a much larger population than Montana, for instance, right? So you might do what's called a weighted average. You would use some kind of mechanical finagling to give extra weight to the Californias, based on their population relative to the whole. And this is very much what happens in a meta-analysis. What a meta-analysis does is it takes different studies that are all studying more or less the same thing, like graduation rate, but did it at different times and in different people and so on, and it combines the results together. And the idea is that maybe you get a more meaningful answer when you combine multiple studies than when you look at any one study. And of course, I've been saying to you this whole time that no one study is enough to make medical decisions. So what's the answer? Well, the answer, if you do this weighted average, is 79% is the high school graduation rate in the US. But there's still a really big question outstanding, right? The numbers in the states were different. They weren't all 79%. Some were higher than that and some were lower. And so you might wonder, are they higher or lower just because of random fluctuation? You just happen to pick people out of a hat and you got 81% instead of 79%. Or are they higher or lower because of systematic differences in what is happening within that state? You can see why that's an important thing to understand, right? Because if one state is really doing a bad job, we can focus on what's going on in that state. If every state is pretty much doing around what you'd expect, but we want to raise the overall graduation rate, well, then we have to do something on a national level. If we can combine all those estimates smoothly, if everything is just kind of random fluctuation, they go together very nicely. That's your fondue, okay? That's your smooth, creamy, delicious thing. If they don't, if combining the data from all those states don't fit together well, they are all coming from different places, you get kind of a lumpy, gross clam chowder. And we're in Connecticut now, so I'll just use the caveat. I'm talking about Manhattan clam chowder here, actually, because New England clam chowder is quite delicious. Okay, so how do you do a meta-analysis? Well, meta-analysis is a study of studies. So instead of the unit of analysis being like the patient who's enrolled in the study, the unit of analysis is the study itself. So you need to find a lot of studies of the same thing. So here's a meta-analysis that was looking at the link between all-cause mortality with overweight and obesity by body mass index, okay? So there have been lots of studies that have asked the question, are heavier people more likely to die? There's been lots of individual studies. A meta-analysis says, let's collect all those studies together, combine all the results, and get kind of one uber result that we can really take to the bank. Now, how do they find all those studies, right? Well, the meta-analysis paper that you're going to read will actually list in their methods exactly how they found all the studies so that you can reproduce it. And they'll list multiple searches, and you don't have to read through this, but you can see all these terms that they linked together, and ands and ors. This is like the most complicated Google search you've ever seen in your life. They used a website called pubmed.gov, but there's a discrete strategy to finding the studies. And of course, there has to be, or else you could kind of cherry pick the studies that you like and throw away the studies that you don't, and then your meta-analysis is essentially useless. Now, here's an example of a meta-analysis published in the Journal of the American Medical Association looking at spinal manipulative therapy with the benefit for low back pain. Okay, spinal manipulative therapy, that's chiropractic, right? You know, cracking the back and stuff like that. There have been many studies of whether chiropractic helps low back pain. And this meta-analysis combined them all. And so what you can see, and you'll see this in most meta-analyses, is something called a forest plot, where each of the lines represent a single study. So you can see this meta-analysis found 12 studies that evaluated chiropractic for low back pain. And what it'll show you is the effect size of each of those studies. So you can see study number 1 had an effect size that slightly favored spinal manipulation, favored chiropractic, but you can see the error bars cross the midline, which suggests that that study was not statistically significant. But as you scroll down, you see the majority of the studies are kind of falling to the left of the line, favoring spinal manipulation. And then at the very bottom, they give an aggregate number, a weighted average of all the studies, just like what we did for the US states graduation rate. And you can see it falls to the left of the midline, which suggests that if you put all these studies together, you conclude that chiropractic is good for low back pain. There's a little secret in this study, though. Only the first 3 studies in this meta-analysis were randomized trials. The rest were observational studies, cohort studies, right? Now we know that randomized trials are the best quality of evidence for causation, and you can see that those 3 trials, none of the 3 of those were statistically significant. Whereas many of the observational studies, which of course can be confounded by these third factors like, I don't know, richer people are more likely to go to a chiropractor, favored chiropractic. So is it fair to combine all of these into one single metric? Is this fondue or clam chowder? Now, there's nothing magical about meta-analysis. Combining a bunch of studies doesn't magically make anything better. If you take the average results of 10 poorly designed studies, you get a poorly designed average. It doesn't improve anything, okay? Meta-analyses that focus on randomized trials are really the best. There often aren't enough randomized trials to do a meta-analysis, like our chiropractic study, which is why you might have cohort studies mixed in. But oftentimes it's a good idea to, at the very least, average your effects in the randomized trials and then average your effects in the cohort studies separately so you can get 2 different estimates. So am I confident that chiropractic helps for low back pain? I'm not that confident. So how do we measure the mixability of your studies, right? How do we decide if your studies are going to combine into a delicious soft fondue or a gross Manhattan clam chowder? So here's just some hypothetical results, hypothetical forest plots. And what I want to show you, and I just made up this data, okay, but it doesn't matter. What I want to show you is, first of all, at the bottom, this big square is the average effect of the study. I combined 4 studies here. So the average effect in both of these meta-analyses is exactly the same. Okay? So the conclusion could potentially be the same. But I reached this average effect by combining these 4 effects. Do you see how they all kind of line up? Like the error bars are different, but they all kind of are falling around the same place. Whereas this average was achieved by averaging these very disparate effects. Okay, so you see the difference there. We got to the same point in the end, but these studies look really weird, and these studies look very consistent. Which mixed better, right? So the top is obviously more compelling because you've studied the same thing 4 times, and you've gotten very similar results 4 times. Like, I feel good about that. Whereas the bottom one, it's what the heck is going on? You know, you got this very strong result in one study, you get a terrible result in another study. These are called heterogeneous studies. They don't mix well. This is clam chowder. This is not heterogeneous. This is good fondue. Now, there's a measurement of heterogeneity. It's called the I-squared statistic. And you don't have to know how to calculate it, but you do have to know how to interpret it. So it ranges from 0 to 100%. 0% say that the studies in this meta-analysis, the results of the studies are different just because of random fluctuation in the tides and the moon and the wind, right? Just slight differences that would be expected because, you know, life is random. Whereas an I-squared statistic of 100% says These studies are all over the map, and not just due to random chance. They are due to fundamental differences in how the studies were designed or who was enrolled in the studies or something like that. Remember when we were talking about the graduation rates in the states? If the heterogeneity across the states is 0%, we'd say, all those little differences between Connecticut and Delaware and whatnot, that's just random noise in the data. This is a national level issue. If you had high heterogeneity, you'd say, oh, no, no, no. The states are really different from each other because of fundamental differences in how they're practicing education. We need to go state by state to figure out what's going on. So it goes without saying, but I'll say it anyway, that a very low I-squared statistic is good in a meta-analysis. It makes you trust the results that much more. One major concern with meta-analyses is where did they find these studies, right? Because they search for the studies in PubMed, and a lot of times you can only find a study if it was published, right? But what if the study wasn't published? What if someone did the research and did the study and just kind of never got around to publishing it? Why might a study not be published? Well, you remember from one of the first lectures of this course that researchers might not want to publish a negative study because it makes their research look bad or it makes their hypothesis look bad. So can we tell that we're missing negative studies? And the answer actually is that we can. And so I want you to look at the left here. And what you see is on the x-axis is the effect of an intervention. That dotted line is the true effect, okay? The Platonic ideal of truth effect. And on the y-axis, we have the sample size. Now, if you have a very low sample size in your study, your estimate of the true effect is going to be further off. The more people you enroll, the larger your sample size, the more precise your measurement of effect size is. That's just part of the nature of statistics. And so if there's no publication bias, what you see is that as the sample size increases, the studies that are published get closer and closer and closer to the true effect size. Now, you, of course, don't know what the true effect size is. It's unknowable. But what you would see is this pyramid-shaped or funnel-shaped, this is called a funnel plot, this funnel-shaped plot that's tapering upwards. And everything is kind of balanced on either side of that taper. Okay. What we see over here is an example of a funnel plot where we think there's publication bias, where some small studies with negative effects are missing, whereas the small studies with positive effects got published, okay? So there's like a missing balance here. So if you see this in the funnel plot, you might say, oh, you know, this meta-analysis is combining studies, but there are studies that are missing, and we need to sort of account for those missing studies. And in fact, there are even statistical ways to fill in those missing studies in a meta-analysis that some people will do. You don't have to know how to do any of that, but when you read a meta-analysis, you'll almost always see some assessment of publication bias, and the authors will tell you whether they think there's significant publication bias or not. So your take-home points for this lecture: meta-analyses synthesize evidence from multiple studies, making them greater than the sum of their parts, usually, but not always. But they depend on the quality of the included studies. The best meta-analyses are meta-analyses of randomized trials, and beware of the two red flags: high heterogeneity and evidence of publication bias. Thanks a lot.